Okay, so let's get started. This is going to be fun. For anybody who's not familiar, this is microcorruption.com. Let's get all the browser UI out of the way now. But Microcorruption is a capture the flag game that was made to both kind of help people gauge where they are and to help people get interested and involved in reversing and exploitation. The very short version that we'll be going over in the tutorial, I think, is essentially the story is that we are hackers and we have access to these IoT locks and we have to break them. All of the code is based around a real-life platform called the MSP430 that TI makes, if I recall correctly. I might be lying to you there, though, but it is MSP430. So, real type of system. All the bugs that we're going to be running into are variants of real-world style bugs. So it's a really neat site. I think that it's probably my favorite thing to recommend to people if they're interested in getting into exploiting software, into reverse engineering, things along those lines. And kind of like with the other thing that Modasano did, the Crypto Pals that I've already talked about, I do kind of have to say, hey, normally I want to go into things blind, but when this first came out, I did most of it. And as such, this is very definitely not blind. I haven't looked at it in a very long while, so I suspect that we will be going through almost as if I was blind. I don't remember any specific answers or anything like that. But I think that it is worth pointing out that this is not completely blind. This is just another one of those streams where I'm coming in unprepared. I haven't been going back and reviewing or anything like that because I want to go into this as fresh as I can so that people can get, as always, just kind of an understanding of like how I would start going about something. And so that said, let's get started with the tutorial. Alright, this will step us through our debugger, nice phrasing, and explain how everything works. Strongly recommended that we go through it. It'll take less than 15 minutes. Sure, let's see. Okay, so there's the story again. Yeah, we've got a bunch of locks. There are Bluetooth connections or IoT things. Using the debugger, we'll be able to step through the lock code, set breakpoints, and examine memory on our own test instance of a given lock. We're going to use that debugger to figure out how to unlock the real locks around the world. So for anybody who's never seen a disassembly, yeah, this is the disassembled object file. Likewise, this is a memory, just the live memory dump. And we have debugger input. It's kind of funny, I've spent a lot of my life in a GDB terminal, and the first time that I used this, I thought, man, they clearly made a debugger that they would like using when they designed this. Yep, lots of scroll back. You're gonna see me using a lot of shorthand commands here just because I don't like typing out full words. So continue, S for step. And I think that I can step out of a function call. Yeah, so continue until the next breakpoint. S is step. We can step over a function or step out of a function, so next or finish. So those are going to be the things that you probably see me doing most. For now, we'll continue. All right, so we have an I/O console and wants us to enter a password. So we'll send test. It told us to. Wants us to continue the CPU. Typically, I would start stepping here. There we go. Invalid password. CPU off flag is set. That means we're done. reset. And right now, I'm just kind of walking through this. There's not a lot going on here. Just teaching us how to use the debugger. Alright, so now we're going to set a breakpoint. Sure, we can break main. For people who aren't familiar, main is one of those common function names. It's typically the entry point for the developer-provided program. You'll often have a little prelude before main is actually reached, but that's kind of mechanical setup typically. So now we continue and we hit our breakpoint. So you can see a breakpoint was set because of this blue background. We can also remove a breakpoint by clicking or add one, toggle them, except right now while it's making me read a thing. Registers, this is kind of one of those things that you're going to get used to if you're working with, you know, CPUs at the debugger level. So program counter, that is where the current instruction is. And then we actually get a live disassembly of the current instruction, which is really, really nice. All right, so now we're going to start stepping the CPU. Yep, so we ran one instruction. The instruction we're on is going to be the red one. Alright, so we're going to step 5A, which throws us into the interrupt. So interrupts are just kind of one of those things that, again, you get used to thinking about if you're working with CPUs. Typically, they are dealing with any sort of I/O, so input, output, that's the most common cases where you're going to see interrupts invoked. The real entry point is start. Yeah, that is thankfully not something that we necessarily have to worry about in the scope of this. Yayindi, while this is Little Indian, it is not. It is not x86. There's actually the reason that they went with MSP 430 is there's a few really nice things about it. Among them, all instructions are always going to be aligned to 2 bytes, which is real A+. Yep, so we've got the console. Continue. We'll follow along, hit test again. Now we can You can also just hit enter and it repeats the previous command, I think. That's what I recall working anyway. Yep, check password looks interesting. So we'll set a breakpoint there. We'll continue until we hit that breakpoint. So, as it says, we are about to move, in this case it's going to be move a byte from at R15 into R14. So we've got dereferencing. So, 439C, got 43, 4390, and then 0, 2, 4, 6, 8A, C. So right here, this hex 74. That's what's going to be moved in. So again, pretty much everything that's being shown on the screen, it really is quite self-explanatory so far. So next we're going to do the test instruction. We're going to test if not 0. It's going to compare R14 with a constant 0, test R14. Then the status register R2, excuse me, is going to be set as appropriate. And here we go, J and Z, jump if not 0. So we're going to branch based on whether or not the 0 flag is set. So right here, we've got the carry flag set. Most modern debuggers are going to give you individual flags. You're not going to have to worry about unpacking a register. It turns out that in the MSP 430, your status register can be shared with just a general purpose register, which is A+. Is a debugger in this game similar to VC or GCC debuggers? I mean, it's a debugger, so kind of yes. So we've processed, like it says, a byte of input. We incremented R12, so we're going to do a thing again. Yep, so what it's pointing out here is that where we've got this J and Z, we're going to end up at at 448E once we do not do that jump if not 0. So breaking there to just allow us to continue. So now that allowed it to just walk through all of its iterations right up until that conditional no longer triggered. And so we are next up at this comparison. So here we're going to be comparing a constant 9 to the register R12. So here we're going to be doing a jump if equal. So, yep, we don't expect to jump. We're going to clear. Oh, okay. So we're going to just start mucking with control flow entirely. So here we're immediately munging the debugger's state. Obviously, we couldn't do this in a real environment, but this allows us some speculative traversal of the code paths so that we can figure out, like, this is where we want to go. So yep, once again, we're testing our 15. And so now we kind of know where the comparison was, and if you've been paying attention to kind of how that flag gets set or not set appropriately, that kind of gives you probably an idea of both what the C code would have looked like behind the scenes and how we're going to be able to break this particular lock. So we'll continue. In this case, it says we were on the debug lock. It's not going to open. And as it says right here, we kind of cheated. So What we did, we wouldn't be able to do, you know, quote unquote, in the real world. But this time, we have a good idea of pretty much what this looks like. This is just letting us know we can give hex encoded input. I'm going to care about that later. We can just wait, step out, and start looking through things. So in this case, as it said, R12 needs to be 9. It incremented once for every character typed, and +1 for the terminal null byte. So in this case, really any 8-character word would work. We're going to put in password like they're telling us to, because it'll probably yell at me otherwise. Now finally, we've got a working in a debugger so far input. So now we can just do the same thing that we did in the debugger. It should work. And hey, that's the tutorial done. So in this case, it wasn't even that it was a password. I suspect that the C code that would have produced that would have looked something like this. In fact, don't even really need to do anything beyond that, because so the C probably looks something like that. It was only checking the length of the string. Alright, so let's play an actual real level then. Yeah, decidability. I'm keeping the code a little bit simpler as a rule, just because I want to make, like I said, I want to make this as approachable as possible. The fact that I just wrote out C code is beginner hostile enough, I think. But in general, that's roughly what we were looking at. Are Boolean true and false 1 and 0 in C? Yes, that is the case. Alright, so here's our first Locket Pro lock. It is not attached to any hardware security module, so I don't even have to worry about it. There's stuff in the manual about that, if I recall. So this is the first series of locks. It's controlled by an MSP430 microcontroller. So there's no default password. Upon receiving the Locket Pro, a new password must be set by connecting to it and entering a password when prompted, and restarting the Locket Pro using a red button on the lock. So we don't have a string section. I do see some English text in the disassembly. Looks like just some statuses, so let's take a look. Let's go ahead and hit C to continue. And we'll just We'll give it 8 A's and just see what happens. All right, so when we're stepping out of functions, adding a certain amount to your stack pointer is pretty common. So here we can see the stack pointer currently points to 4392. Afterwards, we expect it to just, be increased. The fact that we have this visual representation of where the stack pointer points to makes this pretty nice. And then ret, you can think of returning as taking whatever the stack pointer currently points to and putting it in PC. So PC, again, is our program counter. It's the current address of the instruction to be executed. So you can see previously we had 44BA because of the Indianness of this CPU. Now we have 44BA up here in the program counter. What's the playlist that I've got? I'm using di.fm because they've said that we're allowed to use their free streams for background sound during Twitch streams. T. Murdoch, ret ends a function and jumps back to what's on the stack, right? Yes, that is correct. So you can think of ret essentially on this platform as just a pop to PC. So we're going to ret again. We'll end up at 44.4e. All right, so now we're going to move our stack pointer into R15. So the stack pointer as it currently stands is pointing to our input. So let's see what happens next. So we're going to call check password, nifty. So we're going to clear out R14, move R15 to R13. That's fine. We've got 2 pointers now to our input string. And we will add R14 to R13. And we'll compare a byte at R13, which is 439C, 439C, so that's A. We're going to compare it with an offset to R14 at 2400. So let's look at 2400. So we do have a string there. And we obviously didn't equal that, so we're going to J and E in this case. We're going to jump to 44D2, which looks like we're going to clear R15 and return. So now we're going to test for R15. It's 0. And we're going to fail. But the fact that we have some clear visibility into this this memory gives us an idea that maybe this might just be a hard-coded password. So let's reset and try again. So we'll send, step out twice, 3 times. And we'll hop into check password. So we've got this little bit of shifting around of our registers to start, and then we're going to start comparing bytes. So now we fall through. We don't take this branch, so we're going to increment our 14. We're comparing R8 to R14. So let's So eventually we're going to end up at 44CE when that stops being true. So let's go ahead and continue until that point. So what we've done is we've let it walk through this password here at 2400 and compare it with the password that we put in on the stack, or it exists on the stack. We gave it the password starting here at H and ending at this capital Z. And because we have matched the data through and through, at this point we're actually moving a true into R15. And then we're going to ret, which tells me that now this test is going to give us access granted. And that's pretty simple, like really one of those sort of kind of easier things, but you still see occasionally in software having hard-coded strings where it's a password, where it's some manner of access. It feels easy, but it is absolutely not unrealistic. It's not contrived to the point of being the type of bug that just doesn't exist in the wild. So, before I play the same trick again and we move on to the next level, I want to take a quick break, give everybody a shot to ask questions, observations, anything along those lines. Compared to Zachtronics games, more than 2 registers seems like a bougie indulgence. Oh gosh, I've got real bad news for you about modern CPUs. So far clear, you're interested in seeing where this ends up going. So I'm only going to be going through some of the easier stuff. The whole point of this is for me to show how you would start approaching things that are easy, so that somebody who's interested could start building upon it. I don't want to give the answers to everything. I want to give just enough to get people really interested in this sort of thing. Are modern CPUs bougie as hell? Well, I mean, I guess their price tag suggests they are. Oh, I'm certainly glad if it's interesting. This will be going up on YouTube. Every time that I do one of these, they go up on YouTube. I definitely don't want to force somebody to stay up, if it's 3:50 and you need to get to sleep. Don't stay up just because. All right, well, we're gonna do the same thing over again. We were able to copy the input that we had just straight from memory, so we can send it. And yeah, we've got our victory prompt here. All right, so let's take a look at the next one. All right, so we've got the Locket Pro A2. So we've got a new revision. Contains Bluetooth chip. There's no default password. This is hardware version A, contains Bluetooth connector built in and an available port to the deadbolt. Received reports that the prior version of the lock was bypassable without knowing the password. We fixed this and removed the password from memory. Cool, so this one should be harder.
No signs of life.
So once again, I'm just gonna give it, let's say, 8 days, just to see what's up. So we see our stack pointer currently sitting at, looks like 4380C. And it looks like, once again, we've put all of our data underneath the stack, so unlikely that we're going to see any sort of stack corruption in this case. Full step. Return out of 3 functions. And once again, Move to check password, and let's see, R15, I believe, points at 439C, 439C. Okay, so that's our first. So we're going to compare what's at an offset of 0 from 439C to the literal 6E67. And jump if not 0. Plus 1C, which clears. So we're going to return. This looks like we're probably returning false. So a little bit fast to get out of that that function, but I see that we're now just comparing literals, which tells me that that's probably still a hard-coded password, just a hard-coded password that's ever so slightly more cleverly hidden. So here we're going to test. We're going to jump not 0, invalid password. Cool. So we don't need to finish this out. Let's take a look at what was check password. So 44.8a. The nice thing here is we've got a bunch of literal comparisons. And all of these literal comparisons are just jump if not 0 to the same address. I mean, the offset changes because how far into the function we are also changes.
No signs of life.
So, yeah, so here you can see 1C, then 14, and finally we go to check password plus 22. But if we do the math here, this is also 22, so all of these go to the same spot, which is clearing out 14. Whereas here, we just jump directly past that to check password plus 24, where we then would have move R14 to R15, and we know that it's testing R15. So we want these J and Z's to always fail. Yeah, so it looks like we've actually just kind of been given the password. Now, I think all right, 44.8a is going to be where we go. So let's take a look at this in the memory dump as well. 48A starts here. So BF90, 67, 6E. So yeah, we've got GN. It is entirely possible, and in fact I think it's going to be the case, that we are going to have to muck about with the byte order here, just because this is, again, a little Indian system. So here we've got all of our hex encoded input. We're just going to drop that in that way, and we're going to step through. All right, now let's look at 439C. Just right here. So we've got 676E, so this might just be good. There we go. So this one, again, we kind of worked through it a little bit fast. So I want to give folks, again, a chance to ask questions, make observations before we move on, because this is one of those relatively, you know, this is an intro, but at the same time, I want to make sure that I'm not just steaming through this while, you know, while everybody is just sitting there going, what the hell? Welcome in, Skolgan. You have a question. Well, hopefully I have an answer. Welcome in, Impending Disaster. Hope you're having a wonderful evening. Does disassembly give a hint when we drop a password, when we jump just exactly to a failed sequence? Typically yes. If we're going to, if we hit a code path where we're in, you know, especially at this point we have labels on our functions. The functions themselves are very kindly not stripped as it is. When we hop into something, you know, like check password, and then we see an early return from it, usually that's a good hint that we've probably managed to not end up in the correct space. That's not always true. But if we're trying to put in a correct password and we make it through one comparison before we get kicked out of the function, that's a pretty good indicator that we have done things a little bit wrong. But it's always a question of program flow. So right now we're kind of playing by the lock's rules. We're allowing all of the lock's normal logic to just happen. Depending on how we're trying to approach these, maybe we don't want to do that. Maybe we want to, you know, smash the stack or find some other interesting novel way to avoid having the lock perform as expected to begin with. You're trying to follow, but you don't really know what anything means. That's fair. So assembly is one of those things where it's tough. Like, the good news is that once you pick up assembly for one platform, most of the concepts will transfer over to other platforms. Interestingly, nowadays, thanks to Zachtronics, a lot of people can look at this and go, okay, I can kind of see what these things mean. But assembly is definitely not... It's not beginner friendly. It's one of those things that, you know, especially if you want to get into something like, you know, attacking software, specifically binary, attacking, you know, compiled programs and working through them in a debugger and developing exploits for them. Assembly is one of those things that you will definitely end up learning. But there are plenty of very, very successful security experts that, you know, they don't live in that land. There's web security, which, you know, is very much not an assembly-centric thing. There's a whole breadth of topics out there. So if assembly seems like a neat thing, if looking at a program when it's working this low level seems like the sort of thing that would be fun, it's worth it. It's worth taking a look. But if this just looks like something that, you know, is tedious and very, very fiddly, which it is definitely both of those things, and it doesn't look fun, then this one's not it. This one's not, you know, it's not going to be fun if it's not fun. Is assembly a program or a language? Assembly is a family of languages. When we say assembly, we're talking about the overarching family of languages that processors use at a low level. So your computer almost certainly is using an Intel processor. When I say Intel, I mean Intel or AMD, but the architecture underlying it is typically referred to as Intel x86 64 or AMD 64, depending on, you know, the way that you fall on that one. But either way, we would just say it's an Intel processor, kind of as a shorthand. And that has a very particular assembly language. This is based on the MSP430, which is a platform that TI makes. I've said that twice now, and I really hope that I'm not lying, but I'm pretty sure it's TI. But this is based off of a processor called the MSP430, which has a very different assembly language. It has different rules, it has different instructions. In fact, the registers, you see me working with 2 bytes at a time. Your modern computer is going to be working with, instead of these 2 bytes, so 16 bits, it would be working with 64 bits at a time at the register, before we get into extended registers and things along those lines. So when we talk about assembly, it's a family of languages. In this case, I'm saying assembly specifically as shorthand for this MSP430, you know, specific assembly. But if we talked about assembly in a broader sense, it could be all of the assemblies for the various CPUs that you might run into in the wild. And I'm getting confirmation that it is indeed TI. Good. Hey, Tiki, welcome in. And yeah, like Great Bullet just said, it definitely helps to understand how conversions work. Knowing kind of how to convert between hex and decimal is helpful, although not necessary. Nowadays you can just, you know, pop in IRB, say, hey, what is hex 41? And oh, it's 65. What's the, you know, the character representation of that? Capital A. Not as big of a deal nowadays. It's really, really trivial to figure out, you know, what a given value is going to look like. Understanding byte order in your registers will end up being very important. Yeah, you can also just look up the ASCII table. There's a million different ways that you can approach that problem. Eventually, the more you work with it, the more it kind of just stays glued in your head, but not something that's too terribly critical to get started. And yeah, as was just pointed out, you do tend to see things that are obvious a little bit faster if you know it inherently. And I'm trying to, as I go through these, explain a lot of the things that stand out to me. So, for example, in check password here, where we had all of these immediate comparisons to, and I didn't call it out, but like 6E, 6.7, that's very clearly lowercase ASCII characters if you're used to looking at lowercase ASCII characters. Big Indian is the one true Indian, fight you? Well, I feel like Intel has done a very good job of fighting that mindset. Alright, so I'll wait a moment for any further questions and then we'll move on to the next one. Hey, welcome in, Absurdity. I don't think that understanding or not understanding something like this is indicative of whether or not somebody is smart. It's just another skill. Welcome in, Blazin. Do I ever run FF6 anymore? Yes. But for now, we are doing a thing that I do every week where I just kind of walk through some introductory topics. Previously, it's been cryptanalysis. Today, it's reversing and exploitation. So, yeah, if you're interested, hang out. All right, so let's take a look at this next one, Hanoi. All right, so we're attached to the HSM1. We should probably take a look at the manual to remind myself what that means. It's the first of a new series of locks. Bluetooth chip, no default password. HSM stores the password, ensuring users cannot access it through other means. Okay, so that means we're probably not going to see any indicator of what the password is in code anymore. That's most likely what this HSM1 bit is going to mean, but let's go ahead and double check the lock manual. Maybe. Yes. All right, so HSM Model 1. Security module contains a simple interface. All right, so with the interrupt hex 7D, we'll pass a given password to the HSM, and it will set a byte in memory if the password entered matches the stored password. Okay, not a big deal. So I think that there is interrupt listing. So let's double check that one real quick on page 8. Page 8, not chapter 8. Alright, here we go. 7D, interface with the HSM1. We'll set a flag in memory if the password passed in is correct. Takes 2 arguments. The first argument is the password to test. The second is a location of a flag to override if the password is correct. It's good to know. Also, since it was in the index, I do want to point out, for people who are not already familiar with assembly language in general, there is a small reference, 2 chapters of this manual for just kind of getting your feet wet with some assembly in this particular platform. This is a fictitious lock, right? Yes. So this is a CTF that was built by a couple of really, really smart groups of people. And it's specifically built around a platform that people are not used to working in, which makes it a really fun challenge. So if you've already been somebody who's, gone through and found bugs in programs that are, built on the Intel platform, you can still approach this and it's pretty fun. This is a very different experience to living in a debugger, on an x86 machine. But then on top of that, they wanted to make it, relatively realistic in terms of the bugs that you're going to run into. Some of the bugs that I'm not going to be doing on stream because, again, this is one of those things where I want to go through intro material, get people interested, get people feeling like they can start attacking things like this. But some of the later stuff is really, really cool. ASLR gets introduced. You'll be writing exploits that are extremely impressive by the end of this this series of challenges. What debugger is this? You've only used GDB and Immunity Debugger. So this is a debugger that was built specifically for microcorruption. Microcorruption is the name of this CTF. All right, so let's let's just go ahead and so the first thing that I notice here is between 8 and 16 characters, which makes me want to just, you know, not obey that. So let's see what happens. All right, so it looks like, for one, we're allocating a hunk of memory at 2400, which is where my input now lives. So we'll see what happens here. So we'll step out of these. So I'm going to move 2400 to R15. Okay. We're going to call test password valid. Seems good. All right, so we're going to push R4, then we're going to push our stack pointer to R4. So we're going to keep a handle on our stack pointer. All right, so we're going to increase by 2, R4, and we'll decrease our stack pointer. So one thing that's worth knowing, and this is not, I don't know for sure that this is a rule across every platform, but the platforms that I work on, stacks tend to grow upwards. And what that means is that as you put more data on the stack, you're going to have the stack, just in terms of our visual representation here, it's going to be growing up as more stack frames get put onto it. So you'll notice we're subtracting from the stack pointer so that we can then save our spot. We're going to, in general, we're probably going to be looking at, I'm guessing we're about to do a copy, but in general, it's just good to know the stack pointer itself moves. Data on the stack doesn't change until you write to it again. A lot of people tend to think of doing things like popping off the stack, where you take a value and then you put it into a register. It's easy to think, hey, that value's gone forever, but in fact it's not. You can do arithmetic on the stack pointer and reach data that has previously been written to your stack. All right, so we're going to move 0 to an offset of -4 to R4. Which is fine. No effect here, because R4 was 43FC, which is right here, -4. We can see that the byte that stack pointer was pointing to was in fact our offset, but it was already set to 0. I'm going to move FFFC to R14. We're going to add R4 to R14. Okay, so this is one of those things that you tend to see occasionally. This is actually going to end up being a subtraction operation because of the way that integers can overflow. So you can see here we had 43FC, and then when we add FFFC to it, we end up with 43F8. So that's just one of those things that you kind of get used to seeing. All right, so we'll now push R14 and R15, so we're going to be saving those values on the stack. And then we're going to push 7D. So we just referenced 7D as an interrupt that calls our HSM to check a password. And in fact, first argument is the password to test. The second is a location of a flag to overwrite. So now that makes a lot more sense. Previously, we pushed R14 and R15. R15 is your password to test. And that's our first, it's the last one that we pushed onto the stack, which means that it's the first argument that we're going to get. And then we pushed R14 before that. Is that 43F8, F02468 right here. And that's that value that we made absolutely certain was 0. So right now it's 0. Let's go ahead and start stepping. So here's our interrupt. Basically, once we hit the interrupt, we don't really expect much here to matter. In fact, you're pretty much always in the future going to see me just step directly out of an interrupt, because that's just going to call whatever. We're not going to have any control in this interrupt pretty much ever. It's not impossible that maybe an interrupt will contain other code that is vulnerable, but in this case, I'm not going to care what this interrupt does. All right, so now I'm going to move a byte. So offset -4 of R4, so 43 FC. It's this guy. So we're moving that to R15. Makes sense. So R15 is now 0. SXT is sign extension. It's fancy math. Basically, because we worked on a byte, but we want the value to be 2 bytes. We can do that extension. We'll now add 8 to our stack pointer. You're going to see the stack pointer jump upwards, because again, the stack pointer just kind of points to some memory that we can have access to. We're going to pop our 4. We saved that earlier with a push. So that's just cleaning up after the function. And then we're going to ret. So ret's going to throw us back to 45, 48. All right, so now we test R15, which is expected. So if 0, we're going to jump 8 forward. So we're going to test if the password's valid. We'll call puts. I'm just going to step out of puts. You're going to see some stuff on the console. Now we're going to compare the byte hex 88 to 2410. Now, if not equal, we're going to jump, which tells me so we compared a single byte at 2410 to 88, which makes me want to try just throwing, because now we're going to say that password's not correct and we're going to return. And I don't think that we're in controlled data here. We're not. Yeah, we return, clear our 15, and then we're going to stop program execution. So first thing first, let's try just dropping hex 88 at 2410. We can do that because this is all data that we had access to. This is the string that we put in there. So let's try. Just to make sure that my alignment's good, I'm going to throw some B's on the other side of that string. Just a thing that I like to do to make sure that everything aligns correctly. It looks like that hex 88 ended in the right spot. You can see my full text here in that heap that we have at 2400. All right, so really didn't do a ton in this function, this test password valid. So I'm going to go ahead and step out because I think that this next test for whether or not at 2410 that's going to be the one. And there we go. So that's another one of those things where we just need to look for, like, and really keep a map in our head of what the code flow looks like as we're walking through this. So we'll step out. I expect to see that it was correct. So this one is interesting. This is another class of bug that you do see. We were allowed to write arbitrary data beyond what the program expected us to be able to write. And specifically, it allowed us to write to a specific address that it would be directly referencing later. So at that point, we kind of got absolute control over the program once we hit that comparison. So before I solve, I'm going to sit here for a moment. I'm going to sip some tea, maybe have some water, give everybody a chance to chime in with questions, with comments. Stack Overflow. This one is not... so when you hear about stack overflows, what that typically means is that you've ran out of stack space. We actually aren't increasing our stack frame count here. I think that what you might have been referencing is smashing the stack. But in this case, we weren't writing directly on the stack either. We were writing to a completely separate hunk of memory that had been allocated for us. So here, it's neither of those. It's just an out-of-bounds write, which is similar, very similar to smashing the stack or something along those lines, but not quite the same. Zabola92, welcome in. So this is what's called a capture the flag. This was set up by Modisano and Square. And in this particular capture the flag, you get access to a virtual debugger. And the idea is to go through and attack these fictitious locks. Basically, we're attacking computer programs. Trying to figure out how a given computer program can be broken, how we can override the input that that it expects so that we can get it to behave the way that we want. Dwango AC, welcome in. Anybody not already following Dwango, he's got one of the most fun streams on the net and also an extremely nerdy one. If you enjoy stuff like this, you'll probably enjoy the stuff that he does as well. All right. If I don't see any more questions come in, I'm going to go ahead and move on. I think that it was 16 characters that I wanted. That should do it, I think. Yep, we're good. Brilliant. All right, so let's move on. All right, we fixed the issues with passwords, which may be too long. Bummer. This lock is attached to the Lockit Pro HSM1. Lockit Pro B revision 02. New series of locks, blah, blah, blah. No default password. We are using that HSM1 again, so we probably expect that same interrupt that we saw last time. We have improved the security of something. Probably the security of the log. I don't know. Revision notes. Fixed it. All right, so once again, let's not play by the rules. I don't like playing by the rules. There we go. Okay, we can start stepping through. So there, we're now going to call password valid. At a glance, this looks very similar to the password valid function previously. I'm going to save our stack pointer to R4. We're going to bump it up by exactly 1 stack frame. So 43 EC, 43 EO, so it'll be 8 AC. So we're starting with 4524, which I believe is a return address, is what that's pointing to. Okay, so R4 is probably just a saved return address for now. Then we're going to decrement our stack pointer, and we're going to move the byte 0 into a -4 offset from the save stack pointer, which is at R4. You can see the byte that we were sitting at has been deleted. And then we're going to subtract again 4 from the stack pointer. We're going to push these, which again, here we have our interrupt number. We have argument 1, argument 2. You push things onto a stack in the opposite order from what from what you expect them to be used, because they'll be popped off in the opposite order. So you can think of the stack as a LIFO, last in, first out. All right, so now we're going to call an interrupt. Once I actually get focus in the debugger again, we're going to call the interrupt. Just going to step out. All right, -04 to R4, move to R15. So we're at 0. We're going to sign extend. We'll add 8 to our stack pointer. We'll put R4 back to what it was before we did a bunch of munging with stuff. R15 is our return value. And we're going to jump back to 4524, which is that stack address that we saved previously. All right, so now we're going to test R15. We know we're going to jump because it's 0. Password's not correct. We're going to call puts. And then we're going to add 10 to the stack pointer. Okay, so here's our first time that we're going to smash the stack, which is what Great Bullet D was mentioning previously. So here we're actually going to see the CPU stop after I return, because the MSP 430 requires every executable address to be aligned to 2 bytes. So 4141 is divisible, not cleanly divisible by 2, so it's going to jump to 4141, and then it's going to tell us that the instruction address is unaligned. But because we had, and the way that this sort of thing can happen, for example in C, it's just by having local variables. Often those will end up being allocated on the stack because it's very cheap to allocate memory on the stack. So we had a out-of-bounds write on a data container that was assumed to be exactly 16 bytes. And that allowed us to, in fact, when I reset, we're going to keep our eye on all of the data in the stack when I hit continue, and then I'm going to drop out of this input. So here's our stack pointer here at 43 EO. Now I'm going to give 16 A's and then 2 B's for funsies. So now, notice how we had a bunch of, blank stuff that we could overwrite, but these 2 B's overwrote something that actually mattered. They overwrote a return address. So we are gonna drop out. And in fact, what's that 4242? Nothing. Okay, so we're gonna hit unallocated memory, which is fine. Test password is valid. We'll step out of this. It's going to be wrong. Step out of that. And now we're going to add 10 to the stack pointer. And of course we add 16. 10 in this case is in hex. And then we return. You're going to see 4242 is now our program counter address. And it's not an instruction, so it's going to do weird stuff now because it doesn't know what to do. It will eventually hit an illegal instruction or an out of bounds or address unaligned. But now if we think about it, what we really want to do here is we want to unlock the log. So we know exactly where to put a return address that we control. So let's scooch up back to main. Maybe. It's somewhere in here, I promise. Strings, login. Okay, login is where we want it to be. So 4446 is unlock door. Just to double check, should be 4644 over here, or not. No, 4446. We'll just drop back a little bit more. We do have unlock door. All right, well that makes this really, really nice. We can just put that where I put those B's, and hopefully this just unlocks it for us. So we'll reset the lock. We'll continue. Now, in this case, I'm just going to go ahead and be real lazy. Then 4644. We're going to send. We'll step out. We'll step out. We'll step out of the test if password's valid. We're going to test R15. We know that it's not correct. So it's going to tell us, hey, you screwed up, password's not correct. Step out of puts. Then we're going to add 10 to our stack pointer. Stack pointer is now pointing at 4644, which we put in. And then we're going to call return, and we're at unlock door. So there we go. So in this case, again, this is a type of vulnerability that's realistic in the real world. We ended up with a stack that we were writing to without any sort of bounds checking. So we wrote more data than we were able to hold, and the data spilled out into the rest of the stuff on the stack. Well, the stack's real important. It contains stuff like return addresses, which we really care about. So now we just had to write the correct return address, and we're good. No, this is, again, not a Stack Overflow. Stack Overflow is when you have more stack frames than you can allocate. This is just colloquially referred to as smashing the stack. This is just an out-of-bounds write in stack space. But yeah, I'm going to go ahead and take another bit of a tea break, wait for people to ask any other questions. While I wait for people to ask questions, I'll explain what I mean when I say this is not, what we're doing here is not a Stack Overflow. This is what a Stack Overflow is. So here you can see this is a function that almost certainly is never going to return. So if I call this, eventually we overflow our stack. We've got more stack frames allocated than we're able to handle. So that's what it means to overflow your stack. Typically, it just results in an immediate crash. When I say I'm stepping into or out of a command, do I mean I'm doing something specific, or is that stepping forward? So when I say I'm stepping into a function, okay, let's go ahead and just gonna go ahead and copy that so I don't forget it. So here we are currently in the routine interrupt, int. So I could step single instructions, which I'll step twice. First, I'll step to pop the status registers. Then I'll step again, which is going to return. Then I can also say, because we've returned, we're now in a new routine. We're in getSin. I'm going to, instead of just stepping single instructions, I'm going to step out of this function. And that tells the debugger, I have a good idea of what's going to happen in this function. I don't care about watching every single instruction right now. I want you to pretend that there's a breakpoint after this return and just break there. So it's going to step out of that. Now we can step single functions until we get to test password valid. And again, we have a pretty good idea of what happens here. So when I step out, that says, hey, debugger, this is really cool. Just go ahead and finish this entire function and put me back to the calling function. So when I talk about stepping into a method call, a function call, a routine call, that means that we're going into, for example, I will now step into puts. And then we could step, again, individual functions if we wanted to, or we could just step out of the function. How many stacks does Linux allow? That's, and it was just covered in chat, that's a really difficult question to answer without giving you a non-answer. It's going to depend on what language you're using, what runtime of a given language you're using. There are languages that are stackless. So it's an interesting and worthwhile question to think about, but unfortunately it's a question where any answer given beyond it really depends on a million different things is a nonsense answer that would be leading you astray. Hey, Levidence. Yeah. Since I did CryptoPals previously, I figured I'm just going to do everything that Matasano touched, for the start of the series. Because, I mean, CryptoPals was amazing. This is amazing. Of course, now that I've gone through all of the things that Matasano has touched, I now have to figure out what the next thing that I do will be for level 1s, but c'est la vie. Okay, so I'm going to solve this and let any more last-minute questions roll in. And this is going, like I said, this is going at something of a, faster pace than would be expected if, if I've never touched this before. It's been years and years, but all the same, this is something where I have seen it in the past, which helps, especially because we're working on the MSP 430, which is not a platform that is completely alien to me. But on top of that, if I was just getting started in reversing, this would be something that would take me longer. So if you find that this is really interesting, but it doesn't, you haven't solved a level in 15 minutes, don't let that discourage you. This is the sort of thing where you start building muscles and you build experience, and then you get to lean on those muscles and that experience to help you notice things that stick out. Because if we look at any of these instructions, like just looking at any instruction in isolation, it's kind of meaningless until you start forming a map in your head of exactly what's going on. And that's kind of a mechanical thing that you have to learn how to do. I'm not auto-kicking for the phrase debug.exe, so no worries. No, you don't need to worry at all. I'm guessing Twitch decided to auto-link that for you, though. I don't think that exe is a top-level domain yet. Give it time. Alright, let's take a look at... I didn't even look at where I clicked. Let's take a look at this one. Alright, so Lock It All developers have implemented military-grade on-device encryption to keep the password secure. Cool. It's a phrase that always means good things. Lock is not attached to any hardware security module. Alright, so we've got the A, revision 3. Or revision 2, I guess, since 01 was not a revision. That's delightful. Apologize for making it too easy for the password to be recovered on prior versions. Engineers responsible have been sacked. Moose bites can be very nasty. Yeah, .com is a TLD, but I don't think .exe is. Alright, so... we'll just... okay. A lot of stuff just happened. That took a long time to get to the input. And again, let's see where you let me write. There's... I feel almost like I didn't throw enough A's at you. Alright, let me look at the stack real quick. Alright. But we end up growing. Oh, okay. So, a thing that I'm going to reset one more time to point this out. I want to point out right now we've got contiguous memory from 43CO, DO, EO, FO, 4400. So, an important thing to know here, 4400 is our program's entry point. But we appear to be copying data. Oh yeah, you can see we're copying data to 2470. That's that thing that probably took a long time. Okay. Alright, so 10, 20, 30, 40, 60, 80, 90. They're AO bytes. Now show me my stack pointer. Okay, so we're just getting truncated. Fair enough. Which is smart. That's, you know, that's good. I'm glad that I got truncated. But also, I'm overriding, or I've got a bunch of crap. Our program counter has moved stuff, has moved a bunch of its program code. So let's see. Okay, so we're gonna ret. So let's watch our stack pointer here. So 2444. And once again, I'm going to compare D3B7 with an offset from R4. 43FE. 3FE is here. So 1, 2, 4. And we're getting a quick jump if we don't get that correct. So let's do something here. I'm going to look up here. D3B7. D3. So let's grab some of this memory that we have copied away. We've got program code that we're able to run. So I'm going to open up the assembler. We're going to disassemble some code here. There's our object. So we can take a look at this. So here's our comparison that we saw earlier. So if the comparison is not 0, we're going to jump a few bytes ahead. We're going to skip over a call, I believe. Second, I see that we've got some questions in chat. Jeff, what are all these instructions, these opcodes that are not part of 6502? Yeah, this is based off the MSP 430. Do I work in cybersecurity? Yes. Great Bullet DE, thank you for hanging out. I hope that you enjoyed this. Yeah, area selection would make this much nicer. I probably could have just like grabbed everything and threw it in Vim and did it that way, but all right. Let's see. So we're gonna jump 10 bytes ahead, which adds 20 to our stack pointer. So 20 to our stack pointer. We did skip over that call. Yeah, so we did skip over that call. We're gonna pop twice and then we're gonna return. So pop, pop, ret. We're at 444E. So we're going to clear R15. And we're gonna stop program execution. But hey, D3B7, and it was looking at the, I believe, first 2 bytes. So let's double check that. We'll just keep that on hand. Send that in. We'll start stepping. All right, so now didn't look at where that was. Which is not good because it was not correct. So let's actually pay attention to what's going on first. Step. All right, R4 is 43FE, 43F E, going back 24, so 10, 20, 2, 4, D3B7. Am I wrong? Is my Indianness wrong here? I feel like this is correct. Let me double check. I want to read. It was an offset of 24, I think. Yep. No. So D3, B7. Can I do that comparison right here? Nope. Bummer. Yeah, so we're doing the same thing. We're going to end up stopping the program. So maybe it's just an Indianness problem. That's entirely possible. There we go. It was an Indianness problem. So here we've got our push 7F. Our call. Swap bytes on R15. So that binary OR, BIS's binary OR, looks like we're inside interrupt here. Yep, there's our return. And there we go. So it looks like it was actually only looking for a couple of magic bytes at the very beginning. In fact, let's reset and try it again without any of that extra data. And yeah, so that it looks like it was just that one comparison that we noticed in that disassembly that really mattered. All right, so before I solve this, once again, I'm gonna have some delicious tea. I'm gonna wait for other people to chime in The Mass, welcome in. Thank you very much for 6 months in a row. Blazin, thank you for 3 months. Just a reminder, all the money that I get from this stream gets given to the Extra Life charity drive that's linked in my stream info. So the subscriptions make me feel real good, but more than that, they help out sick kids, which is hopefully making you feel real good. I mean, I've been using... I learned VIEX when I was a kid. I think that caring about what text editor somebody uses is kind of silly. Use whatever you're used to and whatever helps you get work done. That's all that really matters. For me, all my fingers have muscle memory that makes it so that when I'm not using Vim, I write colons and I hit escape and then I start writing commands, and those end up in whatever I'm editing. And it turns out it's because I'm an idiot who doesn't know how not to use Vim. Would I consider streaming exploiting Hack the Box VMs? I've heard of Hack the Box. I haven't done anything with it yet. For the content that I'm doing with the level 1 stuff, I want to do relatively simple introductory content. I just happen to know for sure that this is introductory level at the beginning of the CTF here, the Microcorruption CTF. Without knowing what level Hack the Box goes for, it's hard for me to say for sure, but if they've got intro level stuff that I can use to help give people an idea of what it looks like to get started and, you know, kind of like the first step so that people can get on their way if they're interested, then yeah, I'll probably do that sooner or later. Papa Zombie, yeah, just whatever tools you're good with, you should use those. I mean, it's good that they have some retired boxes that have full write-ups on them, but what I'm aiming for is less... I don't want to do tutorials. I want to make it so that I'm showing how I would go about something coming at it, you know, blind or relatively unprepared. This is very much not blind. I did these when the Microcorruption CTF first was released. But specifically, I want very much to avoid creating lectures. I don't think lectures are... Well, I think that they can be useful, but I think that there are enough of them. I think that seeing somebody who hasn't prepared material go and try and attack something is instructive in a very different way from what a lecture is. What career field am I in? I do computers. Some of them are considered easy. Yeah, then I'll probably take a look at them. "19 Raiders from PseudoKid have joined. Welcome in, everyone. We are probably going to go at probably one more machine tonight. Probably won't cut stream after that, but every week I do a InfoSec stream where I kind of I walk through step by step the way that I would approach some relatively beginner-friendly content. So if you're interested in InfoSec, if you're interested in this case, reverse engineering and exploit development, this is definitely a thing that you probably want to check out. This is really approachable, really beginner-friendly. It lives in the browser, which means that you don't have to worry about setting up your tooling for it. It's a great gateway to first steps. All right, so let's solve this one. And I'm gonna sit here, see if there are any more questions that come in. This is not x64. I'll pull up a previous machine. This is actually, as you can see from the 16-bit registers, very much not a 64-bit CPU. This is all based around the MSP 430. We are at the 2-hour mark. Let's do one more. Let's look at Johannesburg. It's a lower point total. Like I said, I want to stick to the easier, beginner-friendly stuff for this stream. Yeah, 16-bit is the future. Alright, so, let's see. Firmware update rejects passwords, which are too long. Cool. This lock is attached to the Locket Pro HSM1, so previously we were looking at another lock that did that. When we see interrupt 7D, we know that we are calling into that HSM. But that means that any of the password checking logic is going to live off of the lock itself. Not a huge deal, definitely something that we can deal with. Alright, so, Locket Pro BO4. No default password. HSM1 stores the login password. Revision 4, we've improved the security of the something because the layout's slightly broken. But something is improved. We know that for sure. All right. So first thing first, they're claiming that long passwords don't work. I'm going to say show me. Show me what that means. All right, so first thing first, I notice that our input is not directly written to the stack. Got 2400 here. Our stack lives at, you know, near 4400. It looks like the stack probably grows up from 4400. So let's step out of that. All right, so we're moving 2400 to R14. Fair enough. I'm gonna move our stack pointer to R15. I don't love that. So looking at the stack right now, I do see we've got hex 11 bytes that are currently just nulled out, which we're calling stir copy. So before we start stepping through this, just looking at this implementation of stir copy, we're moving R15 to R13, so looks like we've got a destination pointer probably that we're going to be, incrementing. And then we're going to jump. Yeah, and then we're going to start moving bytes to where R13 points to. We're going to be incrementing. And then we just have the single JNZ. So one thing that the phrase stir copy should set off alarm bells in anybody's head. Stir copy is one of those functions that really doesn't have bounds checking. str in copy does have bounds checking, so you can't just clobber a ton of data. This is going to start copying data, and it's going to keep on going right up until the end of the string. That first 0 is found. So we're actually going to be copying almost hex 30 bytes over the stack, and we've got hex 11 to spare. So let's start watching this go. You can see the stack is starting to fill with A's. Alright, so now we really don't want to see it continue writing. And we are indeed able to continue writing beyond that boundary. So maybe there's a call later on that exits before we would have gotten to a ret. We definitely do not... We can go ahead and step out. We know that all of our stack has been kind of clobbered now. Hopefully, we just never get to a point where we have to return with any of that data. So test password is valid. We've seen this before. This is just our kind of boilerplate call into the HSM. So I'm going to step out. I don't think that this function is likely to be... I'm just going to step through it. It's unlikely that we're going to see anything new here. But you can see we're just setting up the call, and then we expect the byte right here to remain 0. It would be 1 if things worked, or if we got the correct password. Step out of the interrupt. And that byte did indeed remain 0. We're going to move that to R15. You can see R15, even after the sign extension, remains 0. We're going to clean up our stack pointer, pop R4, and we're going to return. So, yeah, that's the same boilerplate. Nothing super surprising about what happened there. We're going to test R15, and if 0, we're going to jump over that access granted. Bummer. So now we're going to print out that the password's not correct. Step out of that. Now we're comparing hex 90 with stack pointer offset 11. And now if we jump equal to that, we'll jump to... Okay, so this is the bounds check, but it looks kind of weird. Yeah, so here, 45.8c. Oh, okay. So it's not equal. It had a stack canary. Okay, to make sure that we didn't clobber it. All right. So now we're gonna puts. So one thing that I notice here, though, that's bad, is that here, that previous stack pointer, I don't know what it returns to, but let's find out. Let's reset this, because the fact that we're calling in to stop program execution immediately after that puts means that we can skip that if our password is correct, or is incorrect, but not too long. So let's run through it once without it being too long. So 4 A's, why not? So once again, I'm going to step into that string copy. We're just going to step out of that. Password is valid. We kind of know what this does by now, so we're going to step out of that. So now, R15 is 0, not a huge surprise. So we're going to jump over unlock door. We're going to puts that the password's not correct, which is fine. No, let me double check our stack. Let's take a look at the stack pointer. So stack pointer plus 9 or plus 11. So plus hex 10, there's 16 here. Is indeed, it's 90. So let's keep on stepping and see what happens. Let's use an invalid command. So now it does equal that, so we expect to jump. Move 12 up the stack pointer, which is going to jump us to 44.3c, which is itself also stop execution. Okay, cool. We can use this. So, see a question in chat. 8 and 16 character rule. Could a few A's not reach the condition we're really looking for prematurely. Yes. So the A's, as we saw earlier, there was a call onto stir copy, so it clobbers the stack. But there's nothing stopping us from writing that canary value, that stack canary, after 16 bytes, and then we could just write a return address that we want. So let's reset. We're going to go ahead and see if we can redirect to just, let's say, 42 or 6262. Why not? So we know that we want there's that. Then the stack canary was 90. Let's just double up on 90s there because I'm not sure if I got that correct. And then after that, let's say, yeah, there we go. So lowercase b. I want to see 2 lowercase b's in my stack after the stir copy, and I want them to be aligned correctly. There we go. So let's pop over to the stack, 9090, and there's those properly aligned B's. So now we're going to step into test password valid. We're going to step out. We're going to test R15. Again, it's going to fail. So we're going to jump. We're going to put so that the password is wrong. Now we're going to do that test 90 against the 11-byte offset of the stack pointer. And this time we expect it to be equal. We're going to move our stack pointer up, and then Windows going to lose focus. But now we've got a return address. So this is great. So now we just need to know what the address of unlock the lock is, and we are all set. So 4446. So this one feels really similar to the other stack smashing. In fact, there's not a lot going on here. The only thing that we had to do is kind of wade through a little bit more of machinery while the CPU was, you know, dealing with several jumps here and there and some conditionals. But ultimately we got to notice that in our login routine that we had a direct call to stop program execution, but then also just this ret instead of another call to stop program execution. And since we're able to overwrite some data on the stack, we end up being able to kind of bypass the protection that a stack canary is supposed to provide. So let's, I think it was 4446. Let's go ahead and try that. And we're just gonna continue. All right. So again, this is one of those things where a lot of cases like this, it's all about kind of following where any user-controlled input has an impact. So something like this, there was user-controlled input that just lived in a hunk of memory that we had no control over. And then we copied it over some stuff in the stack. We had a protection, we had a stack canary, but ultimately because we were allowed to write whatever kind of data we wanted, we were able to override that stack canary. In this specific instance, this would have been prevented had the stack canary been a null byte, for example. If it was a byte that would have forced the stir copy call to return, there's no way we could have overwrote that return address. But I'm not gonna take a tea break, but I'm gonna wait a moment before we solve this last lock for tonight. Give folks a chance to ask any questions, comments. The most popular architectures I find myself working on, Intel. I really want to learn ARM, but my ARM is extremely weak right now. So I pretty much just live on Intel. A custom stir copy that prematurely exits at a certain character count would help too. So there's a name for that. It's called stern copy. In fact, the man page for stir copy. Somewhere in here should say don't use it. Huh. Yeah. Anyway, don't use it. Because stir copy goes forever, stern copy does not. I have encountered man pages where stir copy came with a humongous warning on them. Apparently, this one doesn't lead with a warning telling you not to use it, but yeah, it tells you, well, if you're a programmer, you're going to be all right. What's the worst that could happen? Do I do any timing attacks using caching? No. No, those are attacks that are immensely impressive, and every time that a new white paper comes out detailing the ways that you can take advantage of modern CPU caches, of speculative execution, things along those lines, I eat that shit up. I love those papers. However, the class of person who is doing that research and learning about that mode of attacking computer programs, it is entirely fair to assert that class of person is literally at the forefront of modern attacks. There are not very many people in the world that you could ask that question that would say yes, that would not be lying to you. Would I recommend NASM as a first flavor into x86-64? That one's tough. I'm gonna be real up front. There's no good way to get into Intel assembly. x86 code, there's finally some good material for it, but it's tough. Read everything that you can, do whatever works for you. There's a bunch of guides out there on like introductions to either reverse engineering or exploit writing in x86-64, but as it happens, the resources for stuff like MIPS, I mean, MIPS being kind of the de facto assembly that you tend to learn in university, helps a lot. And as such, like, MIPS is really easy for me to recommend as a first assembly language to pick up. Or, I mean, something super simple like the MSP 430 is also a very good introduction to assembly by and large. But man, for Intel assembly, it's tough. It's real tough. Because on top of knowing Intel assembly, you also need to kind of start getting a feel for, here's what GCC is going to produce with the O2 flag. Because that looks way different than anything that a person's going to write by hand. let's go ahead and solve this one. That's correct. Cool. So there's a lot more here. I really only tackled the first, I can count, I swear, the first 6, 7 if you want to count the tutorial levels. There's a bunch more here. And if this is the sort of thing that looks exciting to you, do this. It's free. Like, this is a free resource. You don't have to set up any tooling because it lives in your browser, which is one of the reasons that I wanted to show it off and say, hey, people should do this. It's super fun. And it's the sort of thing where the more you work through this, the more you kind of, even in higher level programming, start thinking about, you know, what am I actually telling the computer to do? And it starts to really get you looking at, when you're writing software, thinking about failure modes and the way that you might attack your own code. So even if you don't ever intend to do, you know, exploitation, being able to write an exploit, being able to understand how exploits work, leads to you writing better code. So if this seems like it would be even a tiny bit interesting, I can't recommend highly enough getting into this. Years ago, Matasano, and in this case Matasano and Square, produced some of the most amazing InfoSec learning materials on the internet, period. Between CryptoPals, which is what I covered the previous 2 episodes of this, and then with the CTF, the Microcorruption CTF. They are, I can't think of a better way to put it. They're 2 of the highest quality interactive learning experiences for somebody who's interested in CTFs, in crypto security, and in just security and leveling up as a whole. And they both ended up being very, very approachable to people who are new to the concepts. So both of them are worth checking out. But yeah, hopefully this looks fun. Hopefully it seems like the sort of thing that if anybody who was watching didn't feel like they could get into it, that they could now. Because it's the sort of thing where most people can do this. It's hard. And when you're first starting out learning something super new and super alien, it sucks. But the more you can break down your method of approaching the problem to something that you can repeat, and at least reaching this point where the normal route doesn't work, so now I have to start thinking about how to start deviating from my normal plan of attack. Things like this end up becoming more and more tractable. You'll find yourself making progress pretty quickly.